I'd like to begin by thanking the organizers for inviting me to this exciting conference. So my title today is Mass Renormalization and Vacuum Shift in String Theory, and what I'll be describing is based on these papers by Rojipas and Arnabrudra. So the motivation for this work comes from the observation that if we take conventional techniques in string theory, they have limited use in the study of mass renormalization or vacuum shift. So what I'll do is to begin by outlining the origin of what kind of problems we encounter when we try to use conventional techniques of string theory in studying these problems. So let me begin by writing down the LSD formula for S matrix elements in quantum field theory. Okay, this is the formula. So here Gn is the n-point Green's function. A1 to An are the quantum numbers that these fields carry. K1 to Kn are the momenta that these fields carry. Zi's, or let's come to these first. So MIP, these are the physical masses of the external particles, and these are given by the locations of the poles of the two-point function in the minus k square plane. And finally, Zi's are the wave function renormalization factors, which are given by the residues at the poles in this two-point function. Now, in contrast, when you look at string amplitudes, what they compute can be called as truncated Green's functions on the classical mass shell. Here is the formula. So this is the same Green's function that you saw in the last slide. But now you see, first of all, that the wave function renormalization factors are missing. And the Mi that appears here is a tree-level mass of the ith external state. And finally, we take the limit when ki square goes to minus mi square. And this limit is needed in order that the vertex operator is conformally invariant. Because conformal invariance is a concept that we use at tree level, and we have to take this limit to ensure tree level the worldsheet conformal invariance. So here I have again displayed the two expressions. This is the string amplitude. This is the S matrix element. Okay, we see the difference in the wave function renormalization factor first of all, and the fact that here you have a tree level mass, whereas here you have a physical mass. Now it turns out that the effect of the wave function renormalization is not hard to take care of, but the effect of mass renormalization is more subtle. And it is because of this reason, the difference between Mi versus MIP, that string amplitudes compute S matrix elements directly only if the physical mass and the bare masses are equal, but not otherwise. And of course, in string theory, there are many states which do satisfy this property. For example, BPA states have their masses not renormalized. Massless gauge particles, okay, again their masses are not renormalized. So these amplitudes we can calculate quite easily using the standard formulation. And of course, all tree level amplitudes are fine, because at tree level the physical and the bare masses are the same. Now a common excuse that is often used for not addressing this problem beyond tree level is that we can find the renormalized masses by examining the poles in the S matrix of massless or BPA states which do not suffer mass renormalization. So the idea is that we only deal with those particles in the external state whose masses are protected, and then everything else we calculate by factorizing the corresponding S matrix element. This, however, does not always work, and a simple example of this is SO32 heterotic string theory, where there is a massive state in the spinor representation of SO32, and this state does not produce a pole in the S matrix of massless states, because massless states in this theory belong to either adjoint or singlet of SO32. So you cannot determine the mass of the spinor state of SO32 by simply examining the poles in the S matrix elements of the massless states. So let me now come to the problem with vacuum shift. And this is best illustrated by considering a simple example. We are a simple class of examples. We know that in many compactifications of SO32 heterotic string theory on Calabi-Yau three-folds, one loop correction generates a Phi-Lopoulos term. Okay, this is known from the 80s, and one of the effects of this Phi-Lopoulos term is to generate a potential for a charge scalar phi of the following form. Here C and K are positive constants which can be computed from string perturbation theory, and G is the string coupling. And the fact that this shift is proportional to G square is a reflection of the fact that this is a one loop effect. Now, if you look at this potential, it is clear that the supersymmetric vacuum of the theory is at mod phi equal to G root K, but the conventional approach to string perturbation theory does not tell us how to carry out systematic perturbation expansion around this correct vacuum, and the reason for this is that this vacuum is not described by a worldsheet conformal field theory. Okay? This is a result of a cancellation between the tree level and the one loop term in the potential. So then we can ask, how do we proceed? Now, of course, there are many indirect approaches to these problems which have been suggested. Okay? For example, for the vacuum shift, starting with the work of Fissler and Susskind, there has been a lot of work. Similarly, there have been a lot of work for mass renormalization. But these indirect approaches, none of them really succeeded in giving a fully systematic procedure for dealing with these problems of vacuum shift and mass renormalization. So we will instead follow a more direct approach using off-shell Green's function. Now, for defining off-shell Green's function, we can think of two roots. One is the root of string field theory. This, of course, would be ideal. However, at present, the only consistent string field theory at loop order that we know of are in the context of bosonic string theory. There have been many attempts to formulate a string field theory for superstrings and heterotic strings, but there has not really been much progress beyond tree level. The other approach is what can be called a pragmatic approach, which is to simply generalize Polyakov prescription to off-shell external string states without worrying about its string field theory origin. And this approach, which is known as the operator approach, again was explored by many authors in the 80s. So we will follow this pragmatic approach. The main problem with this pragmatic approach is that once we go off-shell, the amplitudes are not invariant under conformal transformation on the worldsheet. In particular, they begin to depend on spurious data like the choice of local coordinates at the punctures where the off-shell vertex operators are inserted. Whereas in a genuine string theory, we expect that everything should be independent of the choice of worldsheet coordinates, or equivalently the choice of metric on the worldsheet. But if one considers it a little more, one realizes that this is not very different from the situation in a gauge theory, where off-shell Green's functions of charge fields are indeed gauge dependent. Nevertheless, we know that in gauge theory, when we calculate the renormalized masses and S matrix elements, then they are gauge invariant. And one might ask, can the story be similar in string theory? So the strategy then will be to compute the off-shell amplitudes by choosing some local coordinate system at the punctures. The result will depend on the choice of local coordinate systems, but let us accept that. But then at the end, we want to show that when we compute the renormalized masses and S matrix elements from these off-shell Green's functions, they do not depend on the choice of local coordinates. And that is all we can expect in string theory. Now, since these issues are common between bosonic string theory and superstring theories, we will discuss the results in the context of closed bosonic string theory. And extension to super or heterotic string involves replacing the choice of local coordinates by the choice of local superconformal coordinates. I should also add at this stage that the Ramon sector has some additional technical complications which we have not sorted out, have not been able to sort out completely, but they do not seem unsurmountable problems. Okay, their problems look more technical. Now, it turns out that this goal can be achieved only if we impose some additional constraints on the choice of local coordinate system at the punctures. We cannot work with arbitrary choice of local coordinate system at the punctures, and this additional condition is what we will call gluing compatibility. So, here I have tried to explain, this on the next slide will explain what gluing compatibility means. So, let us suppose we have a genus G1 m punctured Riemann surface and a genus G2 n punctured Riemann surface. Then we know that we can take one puncture from each of these and let W1 and W2 be the local coordinate systems around these punctures, with the punctures situated at W1 equal to 0 and W2 equal to 0. Then we can glue them via the identification W1 W2 is e to the minus s plus I theta, where s is a real number which we will let run from 0 to infinity, and theta is a periodic variable running from 0 to 2 pi. And this effectively gives a family of new Riemann surfaces of genus G1 plus G2, but now with m plus n minus 2 punctures, because 2 of the punctures have been used up in the gluing process. Now, gluing compatibility demands that the choice of local coordinates at the punctures of the glued surface of the genus G1 plus G2 Riemann surface that we get from gluing must agree with the one that is induced from the local coordinates at the punctures on the original Riemann surface. So, in other words, when we construct a new Riemann surface by gluing two Riemann surfaces, the choice of local coordinates around the punctures is not arbitrary, but they must be chosen to be the same ones that is induced from the original Riemann surfaces which are being glued. This condition is motivated from string field theory, and indeed it follows automatically if the choice of local coordinate system that you are using is inherited from bosonic string theory, string field theory in the Siegel gauge. So, it is not very unusual to impose this constraint. Now, what this gluing compatibility requirement allows us to do is to divide the contributions to off-shell Green's functions into one particle reducible and one particle irreducible contributions. Now, this is counter to what we normally take pride in string theory. Normally, we take pride in the fact that string theory gives only one diagram at a given loop order. What we are doing here is that we are dividing that one diagram into many components. In other words, we are dividing one modular space into many components and calling them one particle reducible and one particle irreducible contributions. And the idea is that whenever two Riemann surfaces are joined by plumbing fixture, we think of this as two amplitudes joined by a propagator. And so, from this perspective, Riemann surfaces which cannot be obtained by plumbing fixture of other Riemann surfaces, they contribute to one particle irreducible amplitudes. The others will be considered one particle reducible. And one particle irreducible amplitudes have the nice property that they do not include degenerate Riemann surfaces and hence are completely free from poles. So, once the division is made, we can apply the usual field theory manipulations to analyze amplitudes. For example, the 2-point function at genus 1, everything can be declared as 1 pi. Then at genus 2, you can get a set of genus 2 Riemann surfaces by gluing the genus 1 Riemann surfaces by plumbing fixture. Those we will declare as one particle reducible as in here. Whatever is left over will include in the one particle irreducible contribution, and so on. So, then the 2-point function can be expanded in a series expansion like this, with one 1 pi component, two 1 pi components, three 1 pi components, and so on. And this now can be used to partially resum the perturbation series and calculate mass denormalization in the standard field theoretic way. And similar analysis, once you have defined off-shell Green's function, similar analysis can also be used to compute S matrix elements using LSC procedure. So, here are the results that we find. We find that when we proceed this way, the renormalized masses of physical states and S matrix elements are independent of the choice of local coordinate system, even though the off-shell Green's functions do depend on the choice of local coordinate system. On the other hand, the wave function renormalization factors as well as the renormalized masses of unphysical states in string theory do depend on the choice of local coordinates at the punctures. And finally, one finds that the poles of the S matrix of massless or BPA states occur precisely at the renormalized masses of physical states that we compute from our prescription. So in other words, if we take a state for which we could use the factorization hypothesis to compute the renormalized masses, that would agree with what we find from the systematic construction using off-cell Green's function. So the one-line summary is essentially that everything works out satisfactorily, exactly as we expect in a quantum field theory. Let me now turn to the second part, which is to shift the vacuum. How do we proceed using off-cell Green's functions for shifting the vacuum? And let me set up the problem by saying that suppose you have a scalar field phi with tree-level potential given by some quartic term plus higher order terms. And let us imagine that the loop correction, say one loop correction, generates a negative mass square term of this form. So physically, one would expect that there will be a minimum at phi square equal to half c over a g square, okay, simply by extremizing the sum of the two with respect to phi, and of course there will be corrections. The question is, how do we compute physical quantities in this new vacuum? Okay, because this is not a conformally invariant worldsheet theory. And here we will assume that all other massless tadpoles at this vacuum vanish. Okay. This of course is no different from conventional vacuum. Okay. In any conventional vacuum, you have to check that the tadpoles of massless fields all vanish. So here is the procedure that we suggest. Okay. So let us suppose we denote by lambda the vacuum expectation value of phi. Okay. This we will take to be unknown to begin with. We will denote by gamma n string amplitudes in the original vacuum. Okay. This of course is known because the original vacuum is perturbative vacuum where worldsheet techniques are available. Okay. And what we mean by string amplitude is what we directly compute in string theory, which is related to the Green's function by truncating the external propagators. Okay. MIs here are just the tree level masses of the various particles. Now, we will denote by gamma and lambda the string amplitudes in the shifted vacuum. Okay. This is something we do not know, and this in fact is something that we want to calculate. Now, we use field theory intuition, okay, to relate the string amplitudes around the shifted vacuum to string amplitudes in the original vacuum, and the idea is that we should be able to get the string amplitudes in the shifted vacuum by making arbitrary number of insertions of the zero momentum phi fields in the original amplitude, okay, weighted by appropriate factors, powers of lambda. Okay. So this then is our proposal for what we take to be the string amplitudes in the shifted vacuum. Okay. So here is the same formula again. Okay. Now this still does not specify what gamma and lambda is, because lambda is unknown. Okay. And now the idea is that we will demand lambda by simply demanding that the one-point function of the field phi vanishes, okay, namely that the phi field has no zero momentum tadpole. The zero momentum phi field has no tadpole. Okay. So we can set simply n equal to 1 here and choose the quantum numbers appropriately to that of the phi fields, and this is an expression we get, okay, which is a function of lambda. And here I have written the first two terms. Okay. So this, for example, comes from the tree level quartic coupling in the theory, and this comes from one loop quadratic coupling in the theory, and there are various other corrections to this formula. And now we see that when you demand gamma n, gamma 1 lambda to vanish, okay, it requires cancellation between different loop orders. Okay. In particular, the leading order contribution to lambda comes from cancelling a tree level contribution against a loop contribution. Okay. And so by following this procedure, one can get a series expansion for lambda of this form. Now the problem of implementing this directly is that individual contributions to this amplitude contain zero momentum internal massless propagators, and that causes infrared divergence. So here is an example. So let us imagine that we are interested in the 3-point scattering, okay, 3-point amplitude in the shifted vacuum. Now, here is a 3-level contribution to the 3-point amplitude, where you simply begin with a 6-point amplitude on the sphere and take 3 of the external lines to be 0 momentum phi. This amplitude is divergent because in the degeneration limit where these 2 components separate, okay, there can be 0 momentum phi that is propagating in the loop, okay, and that causes infrared divergence, okay, in integration over the moduli of the surface. Here is another diagram contributing to the same amplitude, 3-point amplitude, but this is a torus diagram, okay, where you have inserted 1 external 0 momentum phi. Okay. Again, this diagram is divergent because you can take a degeneration limit and you can have a 0 momentum phi propagating in the propagator. Now, it is clear that these 2 diagrams should cancel, okay, because after all we have demanded that the 1-point function of phi is 0, okay, and hence these 2 parts should cancel. Okay. Nevertheless, in the intermediate stage of calculation you have to introduce an infrared regulator, okay, which is done by simply taking the propagator length, okay, the proper time integration of the propagator in the propagator to have a upper cutoff. Okay. And this intermediate infrared regulator introduces dependence on the choice of local coordinates that you use for gluing these punctures, gluing at these punctures. Okay. And after combining all the contributions at a given order, you have to remove the regulator. And here are the results that we find. So, first of all, we find that physical quantities as well as lambda do have finite limit as the regulator is removed. Okay. This is not so surprising because after all we are adjusting lambda to cancel phi tadpole at every order, and the source of the divergence was the tadpole of phi. The second result that one finds is that the shift lambda that we get from this computation, okay, depends on the choice of local coordinates. Okay. So, if you use a different set of local coordinates to do this computation, you get a different shift. However, what one finds also that the physical quantities like the S matrix elements are in fact independent of the choice of local coordinates. Okay. S matrix elements do have explicit dependence on the choice of local coordinates because you have to do this infrared regulator, okay, but their explicit dependence cancels precisely with the dependence in the value of lambda, okay, that we have at the by demanding the cancellation of the 1-point function. Okay. So, again one line summary of this is indeed everything is satisfactory as we expect in a quantum field theory, okay, because in a quantum field theory if phi was a charged scalar, okay, we would expect that the 1-point function of phi or the vacuum expression value of phi could depend on the choice of gauge, okay, and indeed that is what we are finding here. So, this brings me to the conclusion. So, what we have tried to argue is that even if a full-fledged string field theory is not available, a pragmatic definition of off-shell amplitudes based on the operator formalism serves useful purpose, okay, beyond what you could have normally gotten by restricting to on-shell states from the very beginning. Okay. In particular, we saw that it provides a satisfactory resolution to the mass denormalization problem and also perturbative vacuum shift problem. And there could be other applications in the future which I will leave for the future. Thank you.
So thank you. We have certainly time for questions here. No.
So in addition to regulating the plumbing fixtures, when you're integrating over the moduli space, there will be places where those regulated propagators collide. How do you deal with the resulting mess?
Yeah, the point is in this way of doing it, the regulated propagators will never collide. See, let me, yeah, then let's imagine that we, for bosonic string theory, let's imagine that this diagram is inherited from string field theory. Okay. So in string field theory, you always get vertices, okay, connected by propagators, okay, and all degenerations, okay, come from another propagator becoming long. Okay. So if you decompose a moduli space as you will get, for example, inherit from string field theory, then you will never see collision of regulated propagators. Right? Because whenever two punctures come close, okay, that's described by another long propagator, okay, that is joining a regular vortex to another regular vortex. So when you divide these into 1 pi and 1 pr amplitudes, you never see collision of regulated propagators.
So in the second part of your talk, you mentioned that the shift depends on your local coordinate system.
That's right.
So I'm assuming that, again, the independence of physical quantities of the local coordinate system can then be expressed in terms of effectively renormalization group type? Or should I think about changing the local coordinate system as changing some kind of scale that sets the...
Yeah, I would think that this is more like changing the gauge. Okay. The changing the local coordinate system is probably more analogous to changing the gauge in which you are working in.
But so you're saying that the fact that this lambda is not a gauge invariant quantity, it does not specify a background value of a
exactly.
String geometry.
Yes, that's right.
I see any more? Yes, Charles.
I just wanted to ask, did you try light cone coordinates?
No, I didn't really try light cone coordinates, so that's another possibility one can explore. Okay. I mean, I think for vacuum shift, light cone coordinates may be hard, but for mass renormalization, light cone string theory could be useful.
Okay.
Ashok, you didn't exactly say how you prove these results.
Yes.
And in quantum field theory, there are BRST, there are ward identities that enable you to prove this. Do you have similar set of?
Yeah, basically it's the BRST identities that one has to use to prove these results. Okay. But it's BRST identities not in the standard conventional way because the external states are off shell. So you have to keep track of the extra contribution that one gets because of the off shellness of the external states.
Okay, if there are no more questions or comments, we thank the speaker again.